Hello everyone, and welcome to our Research Week event on the Astrosite and an introduction to space situational awareness and event-based cameras. And today I'm going to tell you how we're using biology-inspired sensors to make space a safer place. Let's go take a look at the Astrosite. So what is an Astrosite? It's a mobile, containerized telescope observatory built specifically for tracking satellites in space junk. Normally, when you want to look at something in space, you need to use an observatory, like this, the Western Sydney Penrith Observatory. It's essentially a building with a telescope in it. What we did with the Astrosite was we realized the cameras that we were using let us operate a telescope observatory in a completely different way, in a way that we can move around easily. So we decided, what if we could put that telescope into a shipping container? And this idea took root. And we went from this, sketch of my boarding pass, to this, the Astrosite. So let's talk a little bit about what space situational awareness actually is. It's all about having an idea of what's in orbit around Earth. Because we've been putting satellites up into space for about 60 years now. And it turns out we've done a terrible job in keeping track of what's up there and cleaning up after ourselves. Now, the amount of objects in space has gotten to a point where it's becoming a danger, both to collisions between satellites and collisions between satellites, space debris, and even crewed spacecraft. Now, if you think about how important space really is to us, it touches almost every aspect of our lives, from emergency services to weather prediction to GPS and communication systems. We really rely on satellites for everything, and we don't do much to protect them. So space situational awareness is all about using sensors on the ground, such as radar and telescopes, to track these objects to figure out where they are. Because before we can even start cleaning up after ourselves, before we can even start legislating and keeping track of what people are doing in space, we need to know where everything is. And that's space situational awareness. So let's take a look at what's actually in orbit around the Earth. This is low Earth orbit. And as you can see, there's lots of satellites there. It's really, really busy. This is where we're putting all the CubeSats. So when you hear about mega constellations of satellites, they go up into low Earth orbit. The International Space Station is in low Earth orbit, and so is the Hubble telescope. It's a critical part of our space infrastructure, and it's getting really, really crowded. This is one we want to watch very carefully. If we go a little bit further out to medium Earth orbit, you'll see there are not as many satellites there, but some of the most important ones that we use every day hang out in middle Earth orbit, such as GPS satellites, for example. Now, if we go out even further, you'll see this interesting ring of satellites called the geobelt, the geosynchronous satellites. Now, those satellites are orbiting around the Earth at exactly the same speed that the Earth is rotating, which means they always stay in the same place in the sky above us. And that's really, really important for communication systems. And this is probably the most vulnerable part of our space infrastructure. They're extremely far away, extremely difficult to replace, and extremely expensive. So tracking where things are up there is of both national and international importance. And space situational awareness is critical to making sure that we can rely on that space infrastructure in the future. Now let's talk a little bit about event-based cameras. They're a class of neuromorphic cameras. And I don't know if everyone knows what neuromorphic engineering is, so let me give you a quick summary of it. Neuromorphic engineering is like the opposite of biomedical engineering. In biomedical engineering, we take technology and we put it into biology to try to solve problems. Neuromorphic engineering kind of goes the other way. We look at how biology solves problems, and we try to build systems and devices, in this case cameras, that work more like biology. We do this to try and get towards the power efficiency and the speed and the reliability and robustness of biological systems. Because generally, they outperform computers and robotics almost every single time. So the cameras that we're talking about today, these neuromorphic event-based cameras, they work more like an eye than a normal camera. A normal camera takes pictures of frames, and you've got to pull them out the camera whenever you need them. These cameras are like the eye in that they're change-driven. When something changes in the scene, only then does the camera tell you that something happens. And this gives some really, really exciting and very, very useful benefits, especially for space imaging. So, when you take one of these cameras and point it at the scene, you don't get any data out. Now, there's actually an event-based camera in that telescope over there. And what you'll notice is that when I move my hand in front of it, you can see the pixels generating information as my hand moves up and down. But when I stop moving, you get no data out. Now think about how useful that is when you want to do something that tracks something that's moving across the sky. or that empty sky that has nothing in it. If you're taking photos of it, you're generating lots and lots of data about something that isn't exciting or interesting. With these cameras, you don't get any data from those pixels. But when a satellite comes streaking through the field of view, only those pixels send you information. Now, this means that we capture far less information, we use less power, and we can be much, much faster. Now let's go to the Astrosite, and I'll tell you a little bit more about how we're using these cameras in space imaging and neuromorphic space. And this over here is the Astrosite. It's a standard 20-foot shipping container with a full mobile containerized observatory inside it. How it works, it has a sliding roof, which slides off when we want to do observations, and a scissor lift lifts the telescope up and lets us point to parts of the sky. When it's done, the lift goes back down, telescopes are now safely inside, and the roof slides back. Now, let's go take a look inside the shipping container. On this side here, we have a door that we can go through. I know it says restricted area, but you can come in. And this is the inside of the Astrosite. It's actually divided into two compartments, an office area and a telescope area behind me over here. Now, the telescope area has the sliding roof that slides open. As you can see, here is the telescope. This part, which is the office, allows us to do experiments when we take this shipping container to the desert. It's actually quite nice. It has air conditioning, it has a full set of computers for up to 3 operators, and allows us to connect to other Astrosites remotely and run a network of these devices. And this really, really makes a difference when you're doing remote experiments. We've also tried to make it comfortable, and we have a couch, which makes observing a little bit easier. Now, let me tell you a little bit about neuromorphic space imaging and how that works. We've talked about the problems of space situational awareness and why we need to do a better job of tracking things in space. And we've also talked about neuromorphic event-based cameras. Now, I'm going to tell you how we put those two together, how we're using these neuromorphic cameras to tackle the SSA problem, and why they give us a big advantage over using conventional cameras. It all goes down to how the cameras themselves work. As we said, the cameras only see changes, but they're also very, very sensitive to changes in light around almost any point along the light spectrum, which means that we can see changes when it's very dark and changes where it's very bright. And that lets us operate these cameras both at night and during the day. Conventional frame-based cameras can't work at all during the day. They integrate the light, and when there's lots of light, they just completely saturate, so you get white images out, pure blank images. Whereas with the event-based cameras, the pixels are looking for changes around whatever light they saw last. So if someone looking at a very bright part of the sky, they'll generate changes if they see something get a little darker or get a little lighter. And one's looking at very, very dark parts of space at night, for example, will do exactly the same thing. And that lets us benefit from both the high speed of these cameras and the ability to see both during very bright and very dark parts of the sky. Now, we can also use the fact that these cameras have a very high temporal resolution. So they're very fast. And those events that come out the camera, we get them very, very, very precise time stamps. So we store that with microsecond resolution. And what that lets us do is actually move the camera and image at the same time. So if you take a normal camera and you swing it around while you try and take a photo, it gets blurry, you get motion blur. With these cameras, you don't have that problem. You can move the camera around, especially if you know the motion. You can actually see very smoothly as you move that camera around the scene. And that lets us, with these telescopes, for example, move the telescopes around the sky and capture as we're moving, something you can't do with conventional cameras. And that lets us do things like follow objects as we see them. It lets us do things like use the focus to try and figure out whether we can detect and classify how bright objects are. Additionally to all of this, we're talking primarily about telescopes here. But keep in mind that these cameras are always designed to be low power as well. And that makes them really, really well suited for space applications, where you want to put these on satellites where you don't have a lot of power, and you don't have a lot of bandwidth back to Earth. So cameras that are high sensitivity, low power, and low bandwidth are perfect for applications in space. So what I've got up here is some pictures of some telescopes. Now these are the telescopes that started all these experiments. These are the ones we used with back in Adelaide about 2 or 3 years ago. And why I like to show them is it really shows you how far we've come from these telescopes out in the field in Adelaide to this, the Astrosite. And if you look at that first panel on the left there, you'll see there's two telescopes on top of each other. The top one has this big black box at the back, and you can see that is actually a very, very expensive, very sophisticated astronomy camera. And it's actually actively cooled, that's why it's so big. It keeps the sensor almost at 0 degrees. On that blue telescope beneath it, you'll see a little camera hanging off the back. That's a really early prototype of one of these event-based neuromorphic cameras. And I like to show the contrast because you can see that's a prototype sensor. It wasn't even designed to do this. And it's competing with these astronomy cameras that have benefited from 40 years of development to get to this point. And yet we can do things with that prototype sensor you can't do with that expensive camera. If you look at that middle panel, you'll see the top camera, the top telescope, has an aperture, a piece of cardboard with a hole in. When we look at bright objects like the moon, for example, the conventional camera, which is so sensitive and therefore can't actually handle how bright that object is, we need to limit the amount of light with an aperture like this. The bottom telescope, however, with the event-based camera on, we don't have to do anything. It can see just as well looking at the moon as in other things at night, but it can do that during the day as well. And then next to that, you'll see a setup that we moved to eventually in Adelaide before we built the Astrosite, and that actually mirrors closely what we're doing here. So let's go look at the telescopes we have here in the Astrosite. And this is the heart and soul of the Astrosite. The telescopes, the telescope mount, and the platform that lifts the whole unit out of the container. Now what you might see here is that we have 3 telescopes, and they're all on the same platform, so they're four-sighted and they can look at the same part of the sky. And they're sitting on top of this, the telescope mount. This is a highly precise robotic telescope mount that lets us point anywhere in the sky with really, really high accuracy. It also lets us move and track objects as they go across the sky. So this stops us having to fiddle and point things manually. We can tell it exactly where to go and what to look at. Makes our life a bit easier. Now you might notice here that we have 3 separate telescopes. And there's a good reason for that. On the first one here we have a normal conventional astronomy camera. Now this one takes really, really nice photographs. But in order to do so, this whole system has to be completely still. It can't move. On the other 2 telescopes, we have the event-based neuromorphic cameras. And they let us do really, really interesting things whilst we move the telescope and catch things that are moving in our field of view. So as a combination, this lets us get the best of conventional astronomy and all the benefits of neuromorphic astronomy. Now these telescopes are all looking at the same part of the sky, so we can do these tasks at the same time. What you might also notice here is a small little fourth telescope actually. It's our little sighting scope, and that lets us get a sense of where we're looking in the sky, much like a pair of binoculars. Now, in the middle here we have a much larger telescope, and this telescope has a narrower field of view than the 2 red ones on each side. And that lets us look at an object with the one event-based camera really, really close up, and that lets us track it more easily. At the same time, we have an event-based neuromorphic camera on the other red telescope here, which is identical to this one on this side. And that gives us a much wider field of view of the sky. So with those 2, we can look at an object and use the middle telescope to track it, and use the red telescope, the event-based camera here, to see all the stars around it, build a star map, and figure out exactly where we're looking. It's this combination of sensors that gives the Astrosite this unique advantage when it comes to space situational awareness. Now we just have to wait for the sun to set. Let's go back into the office part of the Astrosite. Alright, so let me tell you about how this all started. How we discovered that we could see satellites with event-based cameras. And we didn't know we could, to be honest. It all actually goes back to those telescopes I showed you earlier in Adelaide. We just decided to see what would happen when you put one of these cameras on the back of a telescope. We really didn't know what to expect. You have to remember, no one had ever done this before. We didn't know what the data would look like. We didn't know if we would even be able to see anything. And this over here is actually the first recording we ever took with an event-based camera. This is Mars from an event-based camera on those telescopes out in Adelaide. And what you'll see is that it kind of bounces around a little bit. It's that dot in the middle there. And the reason it's bouncing around is because we were quite excited and jumping up and down next to the telescope and we actually saw something. But you might also notice it has this weird sort of oscillatory cycle to it. It sort of rotates. And at the beginning we didn't really know what that was, but it turns out that's actually really significant. That's what they call atmospheric distortion or atmospheric scintillation. Essentially, when we're looking up at the sky, the atmosphere between us and the sky is almost like a liquid and it's moving, and that actually makes it blurry when we look through it. Now with most cameras that's a problem, but with these cameras we're so fast that we can actually see how the atmosphere is moving, and we can actually find ways to compensate for that using special adaptive mirrors. There's a field called adaptive optics, and there's some really exciting applications that we're exploring in that area that came out of this work that was so far from what we thought we could do when we started. So that's the first recording we took, and that night we were playing around, we were pointing the telescope at different parts of the sky, and at some point I was just recording and there was nothing going on, so that's just background noise, and then this came through the field of view. And we had no idea what that was. So really, that was sort of the aha moment of this research, because we were like, what was that? And we had this very lively debate about what it could be. Maybe it was a plane, but we're actually right next to an airport, so there wouldn't be any planes we wouldn't expect. We thought maybe high altitude moths, but why would they light up? And after a whole lot of time, we came to this conclusion that it was a low Earth orbit satellite. And that was the moment in which we realized, hold on a second, we have something really exciting here. And that is where this idea of building telescopes specifically for this, but using biology-inspired cameras to track satellites came from. So it wasn't a straight line. It was just, experimentation that led to this. And we built all of this from those initial experiments. So just to give you a sense of what the data from these cameras looked like, this is a recording of an old rocket body. It's a piece of space junk tumbling around up in the atmosphere. So it's an orbit on Earth. And what we're actually doing here is we're moving the telescope to keep this object in the field of view as it moves across the sky. So that's why you can see there's a dot. Now on the left side of this image, you can see what's essentially a frame, what a camera would normally see. And what you'll see is that dot, it's not very interesting. But on the right hand side, you can see this three-dimensional plot of what the data from our cameras actually look like. It's not a picture, it's this spatial temporal volume. And you can see that dot is actually this column of events out of that camera that contain a whole lot of information about what we're looking at. And we can tell things about the satellite just from that stream of information. For example, we can tell if it's tumbling because we'll see breaks as the light sort of reflects off it. What you're seeing flying through next to it are actually stars as we move the telescope across the sky. So you can see that there's a whole lot of information that you don't capture with a frame-based camera that you can with these cameras, and that is where we get that unique capability in space situational awareness. Now, the last thing I want to show you here is the jewel box cluster. This is a really beautiful group of stars. They're very bright, they're very colorful actually. And what we're doing here is we're moving the telescope around so that you can see the stars, this sort of cluster of stars are moving around the display. On the left, you'll see some frames. And in that middle panel, you'll see the output of the web-based camera. And what you'll see is as we move, the frame-based camera has trouble keeping up. The stars disappear and reappear. So they only reappear when we're stationary, and that camera can integrate the light and make a frame. When we're moving, it can't see anything. The web-based camera actually sees better when the telescope is moving. And that's part of that power we're talking about, is saying if you can image whilst you move, you can do things you simply cannot do with a normal camera. What's great about the Astrosite is that we can do both at the same time. Now, I think it's about dark enough that we can actually go and look at some real data from the telescope right now. Catch you over there. As you can see, the telescope is now up. So let's take a look at some real data. What we're going to do is we're going to point it at Jupiter, and I'm going to show you what Jupiter looks like on an event-based camera. And as you can see, we can see both Jupiter and its moons on both the frame-based camera and on the event-based camera. Now, I'm going to do something that you absolutely shouldn't do around a telescope right now. So, astronomers, please look away. So notice what happened, right? As I was jumping, the frame-based camera, you get all this motion blur, which is what happens when you move a camera. But on the event-based camera, you can see that motion really didn't affect it all that much. We can see the stars as it moved up and down. And that's exactly the reason why we can build these astrosites, why we can take these telescopes and put them in an unstable platform like a shipping container. Those conventional cameras usually have to have a full telescope observatory like we saw at the beginning, a concrete platform with a building on top. Because we can tolerate motion, we can move these around, and we can build a system of telescopes that you can put wherever you need them, whenever you need them. And that's really the power of this whole Astrosite system, and it leverages the event-based neuromorphic cameras that sit at its heart. So, I think with that, let's head back up into the lab, and I'll show you how the Astrosite was made. So the Astrosite, it's a big project, and we have a team of people who are working tirelessly to build new Astrosites and refine the technologies and the ideas. And we all work here at the International Center for Neuromorphic Systems, which is part of the Marx Institute at Western Sydney University. Now, ICNS works primarily on neuromorphic engineering, and we focus on three main streams. Neuromorphic sensors, like the cameras we talked about. We also look at other sensing modalities such as hearing, neuromorphic audition, tactile, touch, and even olfaction. We have another whole stream in neuromorphic computing. How do we build computing devices that work with these sort of neuromorphic sensors and try to get to the power efficiencies of brains and other nerve-like systems for processing information? And finally, we have neuromorphic algorithms and systems. And here's where we try to build algorithms and applications that tackle real-world problems. Now, the Astrosite uses our neuromorphic sensors as a novel application to solve the problem of space tracking and for space situational awareness, which kind of links the two together. So, why don't we go into the lab and I'll tell you how we build an Astrosite and show you the process involved in that. And this is the ICNS workshop. It's a fully equipped electronics laboratory with complete solder stations, mechanical assembly functions, 3D printers. This is actually where we build and test and prepare all of the equipment that goes into the Astrosite, amongst all the other projects we have here at Western Sydney University. And I'll show you some of the equipment that we're working with and how we built an Astrosite to begin with. So let me tell you a little bit about how this whole project started and how we actually built the Astrosite here at Western Sydney University. But keep in mind that we'd never done this before. I don't think it had ever been done before. And all we had to begin with was a sketch on my boarding pass. And what's more, to make it a bit more complicated, the people who funded us to build this said, "You've got 3 months. We'd like to have it at the Avalon Air Show ready for display in 3 months' time." And honestly, it was almost an impossible task. But it's only thanks to the fantastic technical team and all the researchers here at ICNS that we were able to pull this together. Guys like Colin Simmons, Paras Kaki, and Darren Mabel, our technical officers, they pulled out all the stops and really did a heroic effort to get this thing both built on time and under the really, really tight timing conditions that we had for this project. It's through their tireless effort that we actually managed to build something, and on top of that, of the quality that we managed to do. And it's thanks to Saeed, Afshar, Nick Rolf, and Andre van Schaik that we managed to make the algorithms and the systems work to the point that we could demonstrate the concepts and the ideas that made the Astrosite what it is. It truly was an example of teamwork across both spheres of the university coming together and producing something that's really, really exciting and really, really worked to the way we had hoped. Now, actually going from the sketch to something real, it was a bit of an arduous journey. We had really to figure out everything as we went along. No one had ever done this before. So we took the sketch of my boarding pass, fleshed them out into actual diagrams, found someone to help us fabricate the containers, which involved taking a standard shipping container, modifying it, figuring out how to make the roof slide off. In the end, we just used a garage door motor, which worked fantastically well when you come to think of it. Right? Figuring out how to get the telescope to rise out the top. In the end, we used a scissor lift. In Astrosite II, we've now moved on to a much more sophisticated piece of equipment, I should say, to lift it up. But ultimately, it's an iterative design process. And there's something to be said about rapid prototyping for what you can learn. And in this stage of the design, we had no idea how to do it. We figured something out, we built it, and it turned out to work really well. With Astrosite II, we've improved upon that even further. Now, when it comes to actually figuring out how everything works out, telescopes are surprisingly complicated. I mean, this is one of the real 3D models we built for the system to try to figure out if everything would fit. Because if you look at the range of motion the telescope can go through, to try to figure out how big to make the hole in the roof to make sure that it can come out and move, a non-trivial task. And for us, for people who work in space situational awareness, we didn't exactly have the most sophisticated spatial awareness. But in the end, it all worked out fantastically well. And behind me, you can see some of the equipment. It's actually going into Astrosite II. This is the IT and computers that will run Astrosite II here in the lab being tested and demonstrated. So I should say that we actually managed to deliver this on time for Avalon. In early February, a truck came, collected the Astrosite, and drove off our campus. And a few days later, pulled into Geelong in Melbourne and delivered our Astrosite just as planned. It's a fantastic achievement, and I could not have done it without my fantastic colleagues here at ICNS. So let's take a look at some of the telescope equipment we have over here. This is one of the telescopes actually going into Astrosite II. And as you can see, we have to calibrate and test it. And we do that in the lab over here before we send them out. And hopefully, we'll be doing more of these as we grow the Astrosite network. Because our goal is to say, well, if we can put these all around Australia and use them together to track satellites, we can do things that no one else can do. We can, for example, start tracking a satellite as it passes over Sydney and pick that up as it passes over Adelaide and continue to track. We've got some really exciting projects lined up. For example, we have one funded by the International Australian Space Agency to build a dedicated multi-sensory observatory with Selenium Defence in South Australia, specifically to highlight how we can use these novel sensors built here in Australia to track space junk in a more effective way. And with that, I think we should go back to the main area and we'll have a chat about some of the algorithms that we're using on SSA. Before we talk about the algorithms, I'd just like to point out that this is a really active and exciting area of research, and we have a whole host of opportunities for people who want to study in this field. So if you're interested in doing a master's or a PhD, we have lots of opportunities available, including full scholarships. So go to our website at www.westernsydney.edu.au/ICNS and click on the opportunities page. We're always looking for excited people, so please get in touch. We'll get back to you as soon as we can. Talk about neuromorphic algorithms. I'd like to ask my colleague, Dr. Saeed Afshar, who is our expert on neuromorphic event-based algorithms, to talk a little bit about some of the algorithms we're using in the space situational awareness work. Hi, Saeed.
Hi, Greg. I'm Saeed Afshar, postdoc at ICNS. In this video, we're in the top two panels. We're actually looking at the raw events that are coming in from the two event-based cameras. On the left, we have the ATIS camera, and on the right, we have the Davis camera. And as you can see, we have one star that's stationary in both fields of view, and that's the star Canopus, and that's the object that we're actually tracking. While we're looking at this object, we actually have multiple low Earth objects passing through our field of view. And the really amazing thing here is that this is actually getting recorded during the daytime. Another key feature here is that our two sensors are not aligned with each other. They're actually looking at different fields of view with different pixel sizes and different orientation. Yet because of the way the data is actually getting transmitted from each sensor, the two data from the two cameras can be seamlessly combined together to generate a single state that for our algorithms to interpret. And that's represented by the same colors that are shown in the traces in the bottom two panels. As you can see, the single star Canopus is moving up very slowly through the field of view in three-dimensional space, with X and Y denoting the spatial dimensions and T denoting the time dimension. So in this video, we're actually looking at the same field of view as we saw in the other video. Here it's rendered in black and white. And what we see are stars that are moving in uniform field in the background. And that's essentially our telescope looking up at a single point in the sky. But what you see is there's a circle here in the top left panel. In the red circle is actually identifying a satellite, and that satellite is getting tracked through this field of view with the background stars moving diagonally. Another thing that we are able to actually generate from this input is a star map that takes all of the event data that's coming in through the sensor and lays it out into a star field that is essentially impervious to the motion of the camera. In most cases, if we're using a conventional camera and trying to map the sky, any shaking or movement of the camera would actually create blurs and not allow us to image that sky. But when you use an event-based camera, the motion actually helps us by increasing the contrast. And as you can see here, there's moments where the camera moves with a significant deviation. That's actually a moment when the operator is stepping onto the platform and it's shaking the camera in a completely unexpected way. And what we can see is that that results in the movement of both the tracked satellite in the field of view, but also in deformations in the star mapping that can be seen in the two panels on the lower right.
Thank you so much, Saeed. That was fantastic. All right, look, it's pretty dark out there. And I think this is a good time to go to my office and catch up with one of my students who's going to show us how to use the Astrosite remotely. This is our lounge area, our kitchen, and of course, our ensuite mini golf course. Allowed to complete without a mini golf course. Welcome to my office. Let's look now at how we can use the Astrosite in these telescopes remotely. And to do that, I'm going to go to my PhD student, who can show you how he can operate this from the comfort of his own bedroom.
My name is Nicholas Ralph. I'm a PhD student at Western Sydney University in the International Centre for Neuromorphic Systems with the Marx Institute. My thesis is in exploring space domain awareness using neuromorphic event-based cameras. Space domain awareness is about understanding the complex environment of space and what's up above us, natural and artificial man-made. So there's usually satellites, and as a society that relies heavily on space infrastructure, this is really important to understand exactly what's happening up there to mitigate collisions and issues with this infrastructure. And so we use biologically inspired neuromorphic cameras, which have unique capabilities that we don't have with conventional cameras, namely their speed, their efficiency, and a much wider range of observing times. So I'm working from home during the COVID crisis, and from here I'm able to access the Astrosite, which is our remote observing platform, which features high-powered telescopes with conventional, typical cameras you'd see, as well as neuromorphic cameras, and connect to that completely remotely from here, my house, and perform all my experiments, collect all my data. Okay, so I'm going to start our startup procedure. So the sky is clear, wind's not too bad, there's no rain, and it's dark. And I can see on our all sky camera as well that we've got just a tiny bit of cloud or a smudge on our lens, one of those. Okay, so I'm going to open our roof. We have a weather event that we need to reset, that's fine. Okay, so roof open. Okay, and our scope camera will update now to show us what's happening in the observing side of the Astrosite. Okay, so we are open. I can now connect to our telescope mount, provide power to all of our cameras and cooling. We don't need dew heating right now. Okay. All right, and now I will raise our lift. So Greg, are we right to do that?
Good to go.
Okay. All right, raising the lift. Here we are. So we can see our telescope coming up now. Okay, so we look raised. All right, the first thing I'm going to do is just see what we have up at the moment. Okay, all right, so we have slewed the telescope to a nice bright star. You can see here, this is the feed from the event-based camera. On the left-hand side, we have the APS pixels. So these aren't your normal event-based pixels. They actually collect information about the intensity of the objects you're looking at. And then here we can see on the right two images, the event-based pixels. All right, so here in the middle figure, you can see the raw events that we get from the event-based camera, from the neuromorphic camera. And here we have the white dots are spikes, positive polarity spikes, and they're returned when there is a positive change in contrast, but we get the black dots when there's a negative change in contrast. So in other words, you get a white dot when something goes from dark to light, and a black dot when it goes from light to dark. Now here we can see our star in the middle, and we have, it sort of almost looks like it's swirling, and that's the effect of turbulence. This is in the atmosphere. So light, as it passes through the medium of our atmosphere, which has different thermal properties, will deflect, and we sort of get this swirling pattern. And on the right hand side, we have what's called a linear, an exponentially decaying time surface. And a time surface sort of decays slowly. It's almost like it shows longer term effects, because the event-based camera moves very, very fast, and the pixels on this figure here will move a little bit slower. It will sort of decay away. Almost looks like a heat map.
Oh, well, thank you so much, Nick. That was fantastic. All right, so let's take a look at our second Astrosite, Astrosite II. So let's head downstairs to the loading dock outside this building, where we're building the second Astrosite.
Well, I'm Darren Mabel. I'm a technical officer here at the ICNS group. I work mainly on the Astrosite project, which is where we are now. This is specifically Astrosite II. My background is from physics and embedded systems and astronomy, and I came to this project through working on the Western Sydney University Observatory. We're basically making an observatory in a portable facility that we can take anywhere, dump it down, leave it and operate it anywhere from anywhere. Mobility and telescopes generally don't go hand in hand, especially high-performing telescopes like this one is. So it's a challenge to make something like this perform and be mobile. Well, the telescopes that we're using here are fairly standard astronomical telescopes. Any person could go and buy something very similar from the store. The mount is a standard astronomical mount, except it's a very high-end one.
And it's completely automatic, right?
That's right. Yeah, that's the goal, to have to be able to operate it manually, remotely, and to have it be able to operate autonomously as well.
So this is building on what we learned building Astrosite I.
That's right. We've made improvements, and when we started this project, we didn't know how to do it. Nobody knew how to do it because no one had done it before. So we've learned along the way, and we're now working on Astrosite II, and we're very happy with the results so far.
And when you finish Astrosite 3, 4, 5, 6, and 7?
Hopefully, yeah. Hopefully I'm around when we get up to about 14.
All right. So end of the year. So we're back in the lab. This is the space bar over here. And now we're going to have a quick question and answer session. So if you have any questions, now's a really good time to type them into the chat.